So the next example of circular motion we're going to look at is this idea of going around a bank curve. And whether you realise it or not, and you probably don't notice it most of the time, every time you go around a corner in a car, the road is actually banked. It's very, very slight on most curves, like a very small amount. But there is a bit of banking there to assist basically the motion of the vehicle going around the corner. Now, this of course is an obviously exaggerated bank curve. You don't get anywhere near as steep as that. Maybe there are some. I think the classic one is, you know when you're coming down Victoria Road towards Parramatta, and then you turn left to go up the James Bruce Drive, that big loop, that's a very savage bank. That's quite a steep bank, that one. Okay, so there's Bob. I've placed it in the middle of the, car, tyre, whatever that happens to be. Now, because it's making contact with the surface, there'll be a normal force at right angles to the surface. And of course, there's gravity as well. But when you have a look at that force diagram, it's exactly the same as what we looked at yesterday. So actually, travelling around this bank curve is exactly the same as the conical pendulum that we saw yesterday. It's a very, very similar problem. And we'll see the equations end up being very similar as well. Because horizontally, hopefully, we're going to stay in a horizontal circle. Otherwise, we won't go careering off the road or whatever we do. So we know horizontally, we just have our centripetal force, but I'll need a component of the normal force this time. And again, we can play with geometry. If I was to draw in a horizontal line here, I could get alternate angles, and then that would be 90 minus theta, and I could show that that particular angle is theta. And so horizontally, the component would be n sine theta. So n sine theta is mv squared on r, which basically was the same, as I say, as the conical pendulum. The only difference was it was t sine theta yesterday. And vertical forces equal to 0. So we have our vertical component n cos theta and gravity going down. So again, we get the same equation, but instead of tension, we have this normal force, which means we can come up with similar sort of equations. I can create tan theta as v squared on rg. So let's have a look at this problem. And this, cars, it's okay. We can move sideways a bit. Trains are a different story. Trains don't want sideways movement, because if they do, that's when the train gets derailed. So it's actually quite an important problem for railways. They've got to get that banking right so that they know the velocity of the train can go round the corners. So our railway lines, radius 400 metres for our particular curve that we're going around. It's 1.5 metres between the rails, and the banking we've got on this is the outside rail is going to be 0.08 of a metre above the inside rail. We want to find that speed that we can go around the track without sideways movement, without getting any derailment. So there's our problem. So same problem again. There's my outside one. I guess my little red box is representing in this case. But I know it's 1.5 metres up the bank, because that was the distance between our two wheels, or the rails. Well, same distance, because you would hope the wheels are on the rails. And we know it's 0.08 metres up. So from that, we can work out the angle, because we can use some trig and find the actual angle that's banking. So there's our forces. We have our normal force, our force due to gravity. Again, we're going to have to break up the normal force into our components, and we come up with, yet again, the same equations. All those horizontal forces will be mv squared on r, and our vertical forces will be 0. So the same problem yet again. Okay, so back to our tan theta is v squared on rg. But as I say, we can work out tan theta from the dimensions that they gave us. Well, I can work out sine theta, because they've given me opposite and hypotenuse. There's actually two ways of looking at this. Sometimes people say, well, for very small angles, and that's what we're dealing with here, a very small angle, the sine theta ratio and the tan theta ratio is approximately the same. Or we can actually, I personally prefer to actually work out the tan theta, because whilst approximately it's the same, it's not actually the same. So I can work out tan theta. It works out to be 4 over the square root of 5,600. What's the square root of 5,609? Let's see how close that actually is to sine theta for this angle. 74.89. There you go, so 74.89. Now it's a matter of just subbing in to work out what that velocity is that we go around our corner. So we know the other information. We said the radius, we got gravity. That's in metres per second, 14.47. But obviously if we're driving our train, our little speedo, I don't know, do they have a speedo in a train? I guess they do. They know they've got to go around 52 kilometres per hour. 1995, here's one from an HSC where it actually takes into account another force, and that is friction. So it's adding in a resistive force, because when you think about it, we're moving along the road, there's going to be a resistance in there as well, because we saw that back in our linear motion, that whenever we travel, there's resistance in the opposite direction. So this now problem brings friction into our situation. So let's just go through it. So it's our standard problem. We're going around velocity V, radius R, going around a corner C, track's banked at an angle of theta, and the particle does not move up or down the bank, or so we hope, because we don't want any of that sort of movement. We get our reaction force, or our normal force, whatever you want to call it. There it is at 90 degrees to the bank. But now there's a component F due to friction. Now here's the thing with friction. It's directed up or down the bank. Now in their diagram, they put it up the bank, but it could be down the bank, because it all depends on how you're moving. If you're sliding up the bank, friction would be going down the bank. If you're falling down the bank, friction would then go up the bank. And so that's why it varies from minus mu n to positive mu n, because sometimes the friction will be in the positive direction, sometimes it'll be in the negative direction. So it's some constant times that normal force. The sign of F, oh, there you go. So they've defined up the bank to be positive. So we know positive mu n is when it's up the bank, negative mu n will be when it's down the bank. And of course we've got our acceleration due to gravity. The acceleration relate, oh look, wasn't that nice? They even told us about v squared on r for acceleration, but hopefully we would have remembered that anyway. By resolving forces horizontally and vertically, show this wonderful expression. V squared on rg is no longer just a simple little expression that we had before. It's now n sine theta minus f cos theta, and so on. All right. Whilst it looks like an incredible expression to get, we still do it exactly the same way. And they've even given us that hint. Let's resolve them horizontally and vertically. Nothing has changed, but we're going to get components of the normal force, components of the frictional force. I just need to work out where theta is in each of those triangles. In the normal force, it would be down here at the bottom, and then a little bit of geometry means for friction, it's going to be up there in the top right-hand corner. Okay, horizontal force, still circular motion, so it all summed to be mv squared on r. Let's draw them in. We have a component of the normal force going to the left, and that'll be n sine theta, and a component of the friction going to the right. As far as this diagram is concerned, it's to the right anyway. So that'll be f cos theta. We know they will add together to give mv squared on r. So we have n sine theta minus f cos theta is mv squared on r. Okay, let's have a look at our vertical forces. We have components up for both the friction and the normal force, but we also have gravity, of course, going down. They will all sum together to give 0. Now, I need to get this expression. Well, look, I've got n sine theta minus f cos theta, n cos theta. There's our fraction that I'm looking for. I did this an incredibly long way, and I have no idea why I did it this way, because in hindsight, it's really stupid. I said, well, v squared on rg I could rewrite as mv squared on r times 1 on mg, and well, mv squared on r, sort of backwards to what really, I should have started with the right-hand side and just substituted in, and I would have got the answer. But anyway, it's just a what looked horrible, actually, once you resolve your forces, it comes out quite nicely. The maximum speed, which we're calling strangely Vmax, at which the particle can travel without slipping up the bank, is given by that particular expression there. That's what we have to show. We're allowed to suppose that mu tan theta is less than 1. Well, thanks for that. Well, because we're allowed to. Well, no, because look at it. If it was greater than 1, then the bottom of this fraction would become negative. Well, v squared on Rg, how's it going to be negative? Can't be. So it's okay. We're allowed to suppose that mu tan theta would be less than 1. All right, we have to have a think about this. So, it's friction that's resisting the particle moving up or down the slope. Then if the particle is not slipping up, right, because it's saying without slipping up, then friction must be in the opposite direction going down. And it's at that maximum point, and they define friction to be negative going down the plane. So for this problem, friction is equal to minus mu n. Okay. So if we sub that in for what we just found, v squared max on Rg will be n sine theta plus mu n cos theta, and so on. Now the normal forces all cancel. And we've got a whole heap of sines and coses that we want to turn into tan. So really all I've got to do now is divide everything by cos theta. Sine theta on cos theta is tan theta, cos theta on cos theta is 1, and so on. And so there's our answer. And we're going to show that if it is, in fact, greater than or equal to tan theta, that the particle will not slide down the track, doesn't matter what the speed is. You will never slide down the track if that coefficient of friction is greater than or equal to tan theta. So now I guess I'm looking for the minimum speed I could travel. Because it's when I slow down is when I'm going to fall down. So what's the slowest speed I can go without sliding down? And hopefully I can show that this is 0. Because if I've got any value, then there is a speed that I can slip down. I want to say, hey, I'll never slip down this track. So if the slowest speed is 0, then I can travel at any speed and not slip down the track. So that's what I'm basically trying to show here. Friction is equal to mu times n now. Because if the tendency is to slip down, friction will now be going up the slope. There we are, v squared minimum, I've just subbed straight in. I know it will end up being that because the only difference in this problem now is the sign of the friction. So I could just rewrite this straight away as tan theta minus mu on 1 plus mu tan theta. I've just changed the sign where mu is, you'll notice. Okay. But if mu is greater than or equal to tan theta, v squared is less than or equal to 0, well, therefore the minimum is 0. We're saying the minimum velocity will always be less than or equal to 0, or velocity squared. Well, you can't have a negative, of course, because we're talking velocity squared. So if the minimum velocity squared is 0, minimum velocity is 0. So if the minimum velocity is 0, the particle won't slide down regardless. We can give it any velocity and it won't slide down. The circular drum. I love this question. Someone the other day was talking about vertical circles. Do we ever look at vertical circles? Here's a vertical circular motion. Was it Don? Did you ask about the... Anyway, so here we go. Here's a problem they gave one particular year where the circular motion was actually vertical rather than horizontal. So we've got some sort of barrel or drum that we're rotating, uniform angular velocity. Particle P is inside the drum. So when we rotate it, it'll be on the surface of the drum as it goes round. What else have they told us? The radius of the drum, angular velocity, acceleration due to gravity, and so on. So if our little ball bearing or whatever it is inside the drum is touching the surface, there will be a normal force, but that will be directed towards the centre. Because it's be at right angles. Well, when we talk about circles, we always say right angles to the tangent, and we know the radius is perpendicular to the tangent. So that's why that normal force is going towards the centre. Okay. There's also a frictional force, Well, the frictional force will be at right angles to that normal force, and so it'll be going along the tangent. And they've in fact told us that as well, in case you didn't work that out, acting tangentially to the drum. So we're going to resolve forces perpendicular to and parallel to OP. Find an expression for F on N. Right? Because the beautiful thing about this problem is I can rotate the problem. And so whilst these normal forces and frictional forces are at angles, that's just some random point in the problem. At some point in the problem, visually, I will see friction being horizontal and the normal force being vertical. But the problem is the barrel is going anti-clockwise, which would be an equivalent problem to the ball bearing going clockwise. However, gravity is no longer vertical. Slight problem, yeah. But that's all right. I can just have components of gravity now that are in my new horizontal direction and a vertical direction. Yes, there is such a thing as horizontal gravity. There you go. So let's put those components in. Bit of geometry, we can work out where theta would be in that triangle. So I'm reluctant to say forces vertical, because it just happens to be for this problem. So I'm saying forces perpendicular to OP, or actually this would be the horizontal ones, wouldn't it? And they're equal to 0. So there's Bob. What do we have? We have friction is totally horizontal now, but there is a component of gravity. So we get mg cos theta minus the friction is equal to 0. Let's have a look at parallel to OP. That's the circular motion because we've got a vertical circle. So we have our normal force and our component of gravity. I've got an expression there. So I have an expression for friction. I have an expression for the normal force. They wanted an expression for friction divided by the normal force. And so there it is. This idea of rotating the problem can come in very handy, actually. I could do it with the classic bank curve problem or the conical pendulum problem. Again, I could rotate the problem so that the tension is completely vertical or something like that if I wanted to work out tension. Okay. So the classical problem, there it was. Bob, whoop, normal force, gravity. And there's friction. In my problem, I put it going down. But again, as I said, it could go up, it could go down. But I could rotate it and make the problem look like that. It's still the exact same problem. But now I've got a component of gravity. I also now have the resultant force has two components. Remember, the resultant force still has to go to the center of this circle, like so. So when I rotate the problem, that's now going off at an angle. And so when I'm resolving horizontally and vertically, it now won't be 0 and mv squared on r. It'll be a component of mv squared on r in both. And theta would be in there. So what I could do with that problem is I could now say, hey, I'll resolve along the bank, and just what everything looks as if they're horizontal. Friction now is totally along the bank, and mg sine theta. And we get it straight away. It just drops out straight away. Friction plus mg sine theta is mv squared on r cos theta. And the normal forces, they would resolve to be mv squared on r sine theta. And you get the normal force. But yeah, so anyway, that idea of rotating the problem can sometimes come up with these expressions a lot quicker. So you're basically isolating the force you want to find and making it purely vertical. Because the wonderful thing about friction and the normal force, they're always at right angles to each other. Okay. So Cambridge 9C, not to be confused with the Patel 9C, because the Patel 9C was actually on conical pendulum. 9D in Patel is on the bank curve.